is CHEM676. The goal of the course is to describe properties of materials through computational modeling, and we need to sacrifice part of the time to the theory background, because at the time when some of us will apply these skills to research projects and probably publishing papers, one needs to justify what is being done, and it is typically done by quoting right equations. So congratulations to everyone with completing the presentations last time, and the plan for we are starting next chapter, density functional theory. The meeting today will, as usually, have some theory background materials, and it will be in some sense transitional meeting from Hartree-Fock to DFT. So I will partially complement what you were presenting last time on the observables. So I will try to focus how to convert successful electronic structure calculations into observables that characterize materials, and then make a transition to the so-called density functional theory. So in this chapter, which I think we will be able to complete during the summer for sure. So 1 week, 2 weeks, 3 weeks, 4 weeks. So the same in the parallel with the theoretical background, we will learn practical skills with the new software called VASP. And since semester is summer semester is so short, I suggest we expedite calculations of the getting the skills on this software, and do presentations a little earlier before we complete the theoretical background. So on the two Mondays from now, I suggest we will do presentations. And if any of the class attendees have challenges with Monday in 2 weeks, please let me know. If there are no signals, I will assume it is approved by everyone, and next time I'll probably distribute the sign-up sheet for the materials. So basically, we will have in the 4 next meetings, we will cover 4 basic subjects that later will be presented on this presentations. So number 1, how to convert the geometry into specific format for VASP, so preparing input file. Second, how to plot density of states and orbitals in the VASP software. Third, how to compute absorption spectra. So it will be next Monday if you specifically need this. And the fourth, how to prepare and run molecular dynamics. So there are some additional skills, but because of the semester is short, we will maybe do it as a during next session. So these 4 skills needs to be completed, and then we may start the mini research projects. Okay, so what are we going to do? Let me.
Excuse me.
Yes.
I have a question.
Yes.
I have a question.
Yes.
The question is that, so in all purposes, like for calculation and optimization, all purposes, like Gaussian 09 is better or any other software like Jaguar or other softwares better? We can use all the time Gaussian 09. That is better, right? All the time.
If you have access to Gaussian 16 on CCast, it is better.
Okay.
And Gaussian is designed for the small confined molecules. If if you need to describe molecules embedded in liquids or periodic solids, then there is another software that we will start today. So depending on which project you want to do. And by the way, please start thinking and designing the mini research project that you want to explore with computation, because this semester is shorter than usual. As soon as we do presentations on WASP skills, we will start mini research projects in the lab time. Joanta, did I answer your question?
Yeah, that's fine. And another question: suppose I want to optimize one structure. Suppose one chair form, one board form. So how I will get the proper optimization energy, like lowest energy for like stable molecular state? Suppose
The latest
I want just let me finish.
Please.
Suppose I want to draw one chair conformation of cyclohexane and both conformation of cyclohexane. So we know that chair conformation is more stable than both conformation. So my question is that how I will optimize properly in which software, which basis set that I will get the proper optimized structure like D3LYP, RTFOX 631G or 6311G plus DP star star. Which way I will get the proper optimization of best and lowest energy, like best stable molecular structure?
The question is very appropriate, and typically researchers write papers on that. So one tries to optimize it with different functionals and report which one seems more reasonable. So it is a more research question rather than standard protocol.
Okay. No. My question is a completely research basis. Suppose I want to optimize one chair form of cyclohexane and then boot form. So how I will optimize in with help of Gaussian? How?
Oh, it's a standard job. You already were reporting it in your presentation. Just select optimization and run job, and then take the last geometry after successful job.
Okay. So only I can use only Gaussian or Gaussian 09, and then I can easily through energy and I have to report the energy like RHF, right? And then easily I can tell that which this molecular state is more stable and how much energy, like atomic unit to Hartley, that I have to convert to kilojoule and kilocalorie. Then easily I can interpret that this molecular structure is more stable than this. Definitely through use of Gauss or Gaussian or maybe Avogadro, I can use any software and I can predict the exact and stable structure, right?
You are correct, but when you are doing this way, you need to specify which functional, which basis set you were using. Because when you use modify basis set and functional, the geometry that comes after optimization can be different.
Oh, okay. Now getting. Suppose I want to use the perfectly suppose one basis set like 61G basis set B3LYP, and then I can optimize and I can write my structural energy. So I think anyway, in any platform, I can write my energy, right?
Yes.
So means just I have to see in any software that what could be the particular and perfect stable molecule that I'm getting from those particular softwares. Which basis set is giving me perfect and stable energy. means lowest energy, right?
Mm-hmm.
I have to check different basis set, and then I have to calculate which basis set is giving me proper and exact lowest energy, means stable state. Then I can write it in my project, means like publication purpose or project purpose, right?
Exactly, exactly.
Okay. So maybe I can use, suppose I am using Mac OS. So I have MacBook Air. So in suppose when I will use my Gaussian 09, so definitely I will write previously those same thing, right? Through using um, those means how I'll like instead of mobile extern, I have to use this, right?
MobiX term is only a communication tool. It's not a computational tool. It's a way to connect to a server or cluster.
Okay, so
Jointe, let's set up at Jointe. I apologize. Let's set up a time for discussion after we go through materials, because other participants of the class may have plans for the evening, and we need to complete certain amount of material.
Okay. We can start. Yeah, thanks.
Okay, yeah, but thank you for the questions, and I'm very happy for your interest.
Thanks.
Okay, so when we did by now we have completed Harry-Fock, and we need make a transition to new theory that will give different results and is more appropriate. So the main goal of any computation is total energy, and when we are using the concept of Hardy-Fock with molecular orbitals, the total energy is composed as orbital energies of occupied orbitals. So two electrons sitting on each orbital if there is a closed shell, plus the additional contributions to the energy because of the Coulomb, which is positive, and exchange, which is negative contributions between pairs of orbitals. And the equations that are being solved is equivalent to, well, are related to the diagonalizing so-called Fock matrix, which includes this Coulombic interaction between different atomic orbitals residing on different atoms. So if one would look into the manual for the Gaussian software, they would rewrite this expression for the Fock matrix in the following way. So the core part, which would correspond to kinetic energy of one electron and attraction of electrons to nuclei, and then electron-electron interaction is written in the terms of Coulomb and exchange interaction between atomic orbitals, which are labeled by these Greek letters. And since we need interaction between molecular orbitals, this P, the object capital P with two indices, lambda and sigma, includes products of the expansion coefficients of molecular orbitals from atomic orbitals. So molecular orbital is coefficient, I'm skipping summation and indices, and atomic orbitals. And since in each interaction we have pairs of molecular and atomic orbitals, we need to have this C coefficient twice in the second power. So the if you do not if you decide what to focus your attention on and what not to focus right now is something that we will use later. For the sake of time, I'm not bringing it for everyone to feel, but when we will be going over density functional theory, I will offer the same flow chart to be filled by all participants of the class. And at the end of each chapter, we have such flow chart. So when we were finishing the geometry optimization, we had a flow chart for browsing through different space and different points on potential energy surface. And after several cycles, one is getting best geometry. Right now, we are about to finish Hartree-Fock, and we are browsing in the space of expansion coefficients of molecular orbitals over atomic orbitals. And we need to find these coefficients. As soon as we find right coefficients, we declare success. In the next chapter, we will be optimizing the so-called concept of the so-called total density. And in each chapter, we do have this self-consistent cycle. So the self-consistent cycle for Hartree-Fock and is here, and it was written by students from previous semester. So as an input, one places in the coordinates and tolerance limit, then one makes a guess of molecular orbital and forms Fock matrix in the basis of initial guess molecular orbitals. Then one diagonalizes, finds eigenvalue problem with this Fock matrix and finds new expansion coefficients, and computes the total energy according to the equation a couple of slides ago. And then if the total energy becomes smaller than tolerance, then one reports total energy and tells that the job is done. If energy is large enough, one repeats this cycle once again. So here is the same flow chart in the better typed fashion. So one starts from positions of ions and ends with total energy and observables. So it is what we see as an input and output of our Gaussian calculations. In between, one creates this P object, which is called density matrix, uses it to formulate new Fock matrix. Then this Fock matrix is being diagonalized, finding eigenvalues, and upon finding matrix elements in the basis of this new expansion coefficients, when one finds total energy. Okay, so observables.
I think, sorry for disruption.
Oh, please.
Dimitri.
Yes?
I think you could wait a little bit time because I think Mahima could be joining.
I will share recordings, but since summer semester is about 25% shorter,
that would be better, yeah.
so yeah. we better, well, you do not need to rush, but I need to rush. So let me bring a discussion I'm going to ask, what is light? So, Janice, would you like to give your vision? How do you understand, or how you can interpret what is light? And if the diagram on the screen makes sense to you, you can comment on it. Okay, no answer from Janice. If you were answering, your microphone is muted. Let's check with Kristen. And
light is a form of electromagnetic radiation in the form of like a wave and a photon, or in the form of photons, which are behave as particles and waves.
okay, okay. And may I ask you to read my mind? Why we need light in this course? Why the electromagnetic radiation is important for characterizing properties of materials?
Does it have the more an effect the displacement of an electron?
Yes. So yes. So which types of materials characterization you can bring up? Like if you have a like beaker with substance and you want to characterize it, which characterization?
Electromagnetic fields to separate and identify the different parts of the.
Which one? Which one?
Well, you could use electromagnetic radiation for lots of forms of spectroscopy in order to then characterize the molecule or your system.
Okay, okay, yes, thank you. Joanta, would you like to complement this discussion and tell which characterization techniques you typically use when you have like test tube with a specific substance?
Suppose in my view, like light means that natural agent. Natural agent means like that stimulates sight and makes things visible, like UV visible spectra you are getting. How? Light. So it's an electromagnetic radiation. Like E is equal to h nu. So energy how will get Max Planck constant into nu.
Okay,
Frequency.
okay,
So
okay.
light is equal to dual particle and wave nature. So means it's a duality. It's a sometimes it's wave nature, sometimes it's particle nature.
Okay, okay, yeah, yeah, enough.
Light can make things visible, like invisible spectra you are getting, like ultraviolet ray, visible spectra. How you are getting? That's completely in visible light, sunlight, completely sunlight. You are thinking sunlight. How? It's a visible thing, right? So the natural agent that stimulates sight and makes things visible is equal to H. It's a wave particle duality. Simple thing.
Okay, okay, thank you. So you've mentioned a very good thing, UV visible spectra. So each substance has its spectral signatures, and
Yeah.
So the electromagnetic radiation is a way to probe properties of materials, and
Yeah.
NMR is also irradiation of substance with electromagnetic radiation of very low frequency, very long length. So it's
Yeah, it depends. Actually, completely it depends on frequency and energy. Suppose in frequency and energy, I'm telling you have to completely understand frequency and energy because your visible light and like IR, suppose infrared, microwave is completely depends completely in energy and frequency. So visible region means sunlight.
Super,
The
super.
natural agent that stimulates light and makes them visible.
Excellent.
Visible.
Yes, yes, correct. And even if the molecule is not close to us, if it is in the far galaxy, we can do astrospectroscopy and characterize objects that are very far from us. So, what is shown on this diagram? How would you interpret these arrows and oscillating functions?
Like this is the cos and sine mixture, right?
But what is the physical meaning of this green and red? Oh, sorry, blue and red arrows.
It's a magnetic moment.
Not moment, just magnetic field.
Magnetic field.
Uh-huh. So, you very happy to see you connected. So we are exploring how to convert outcome of electronic structure calculations into properties of material, into spectra. So electromagnetic wave is, if it is a plane wave, monochromatic plane wave, it is a electric, which is red arrows, and magnetic, which is blue arrows fields, and it propagates periodic in space and time. And this imaginary exponential is a typical way to describe it mathematically. And
I think it's a mixture of electric wave and magnetic wave. Right?
Yes, yes. So what is electric field? Joante? What is electric field?
Electric field means what I can say, like it's a surrounding that generates electricity. Means that will generate electricity.
Okay, I would. Yeah. So it is the reason why charged particles start to move. Why the force? It's a reason for the force.
Yeah, like, you can tell that a region, like the charged particle or maybe object, like force could be exerted through electric radiation or maybe other things, like through charged particles. Means like you can generate a force field, like you can generate a with which a force could be exerted, or maybe force could be generated, or maybe light could become like that. Maybe electricity could be generated.
Okay.
That is the electric field.
Okay, very good. And now here is a paradox. Most of the molecules are neutral, right?
Okay, so you have to generate electric field. You have to generate field. That could be a combination with magnetic field and electric field. So
but
that field will be generated, and then you can get some force.
But here is the question: if the molecule, logical paradox, electric field acts only on charges, and most molecules are neutrals. Neutral. They have equal amount of positive and negative charges. So how the electric or electromagnetic field can interact with a neutral molecule?
You cannot generate without without polarization. You cannot generate electric or magnetic field. Polarization is important. Like you have to polarize the molecule, right? Otherwise, field will not be generated.
Okay. And I see that Kristen unmuted the microphone. Do you have a comment?
I was just going to question if dipoles would come into effect with the electromagnetic field.
Yeah. Yes. Thank you. So even in neutral molecules, we have positive and negative charges that can be displaced in space, and then electric field will act on a dipole and make it to rotate, right? To orient in space.
So means definitely you have to create your polarization, right?
Yes, you were right as well.
So that's why, yeah. That's why that's why Raman spectra came through this way.
Yeah, exactly. Yes.
Yeah.
Yes. Janice, if you like, you may give a comment. What is a dipole? It's high school physics. Like, can you define what is dipole? If you want. No, we do not. I do not hear you. Yeah, let's wait a little. I see the microphone is oh, okay. Janice did unlocked and logged in. One may try to log in with different browser. Janice, I see you have reconnected back. So if microphone is not working, but you want to give a comment, you may just type it in. Okay, and while Janice is trying to fix it, may I ask you what is a dipole and what is interaction between electric field and a dipole? Okay. I don't know what I see. I see it. A dipole is a differentiation of charge over a surface.
No, I am not agree with it.
Okay.
I think in my view, suppose dipole means, in chemistry purpose, I am telling, dipole means a molecule in which the concentration of positive charge is separated from a concentration of negative charge.
Okay, okay. I like it very much, and I like that we have a scientific discussion here. So yes, and the as Joanta defined concentration of positive and concentration of negative, I would say center of positive and center of negative charge.
As like you have two equally distributed positive end and negative.
So
that's
if
that's the equally like hydrogen. That center is there. You equally have to shift some positive end, some negative. HCl, that positive end and negative end. That creates a dipole.
Okay, okay. And one sets up if they are separated in space, one can set up a vector distance from positive to negative. And basically it will be
vector field. So you can choose a vector field. Yeah.
Vector.
Like completely physics. You have to come back with physics.
Okay, okay. And now the next question. I didn't think that. Okay, yeah, thank you, Janice, for agreeing. Now, next question. What is the interaction? What is the energy of interaction between electric field and a dipole? You do not need to describe it by equation, but just say or type by words. So if the dipole and electric field are collinear, so if the vector of the dipole is parallel to the vector of electric field, then the energy is minimal. If the dipole is rotated and made perpendicular, deviates from this direction, the energy becomes bigger. And in some sense, the energy of a dipole in electric field depends on the angle between dipole and electric field, angle theta. And
yeah, I'm agree with you, but the thing is that I'm thinking one aspect here, like suppose you want to put any electric field within any molecular atmosphere, suppose in greater mass, in positive nucleus of greater mass, and then an applied electric field may also generate such a charge displacement, right? Creating an electric dipole, momentum of the atom.
So
and then this field will interact with another dipole, give rise to force between the two dipoles, right?
Okay, so Joanta, you are describing a sequence of processes. And I'm asking only instantaneously. If we already have a dipole, we do not move anything. We just assess the energy of interaction.
Yeah, definitely. So suppose you have to put the electric field, and then already the positive end will go to negative end, and negative end will go to positive. That interaction definitely will come, right?
So if the dipole,
and positive repulsion, definitely.
it's well, I wouldn't say repulsion, it's just rotation. So
yeah, just rotation.
If the dipole and electric field are parallel and collinear to each other, then the energy of system gets smallest, so it's negative. And the dot between dipole and electric field corresponds to scalar product, which means absolute values and cosine of the angle between them. Mu E times cosine theta. So this is all classical high school physics, but the same principle is applicable to molecules interacting with electromagnetic field. So
So I think you know the cos 0. Go to previous slide.
Yes.
Yeah. Go to previous slide.
Yes, I did. It takes a little
Yeah.
delay.
Here. The thing is that when you cos theta, like cos pi, any cos t or maybe cos sigma t, cos pi t, cos delta t, any cos t is when if any function is equal to cos 0 is equal to 1. So in this portion you have to start with cos 0 is equal to 1 means like suppose x and y axis you have to start with 1, and then this is like a sine function, but you will calculate with cos function. Cos is like that will be started from 1, cos 0.
Exactly. And then
it's
you
not sine function. Like sine wave means like sine 0 is equal to 0, cos 0 is equal to 1. So definitely you have to start with x, y axis and then y from 1. Start from 1, not 0. I think so.
Yes, and we have a minus sign. So when they are collinear, it will be negative. So
yeah, definitely that is okay. But the thing is that you have to start from first in cos function. It will be started from 1. And
yes, exactly. When they are parallel, the angle is 0 and the cosine is maximum. Yes, I have no doubts that you agree with this.
Yeah,
so here is the same equation. So energy of molecule in electric field gets smaller, gets this minus electric field vector times dipole. And if the molecule does consist of several ions, each of which has positive charge of Z capital sub I. So everything except proton has a larger positive charge. And so many electrons are lowercase sub I lowercase. Then we can calculate the dipole as according to the words of Gianta. So average position of all positive minus average position of all negative. And then we are going to practice this idea in the basis of electronic structure. So we are considering an example when we do have a molecular system with several orbitals. So it could be hydrogen molecule, hydrogen atom, or something different. I'm not going to focus on the details. We look only on the 3 orbitals. Lowest one, which is occupied, and no, two lowest orbitals are occupied, and then one E3 unoccupied. So according to what we got in this Hartree-Fock theory, the wave function is a Slater determinant. And we do know a protocol how to convert wave function into expectation value of certain operator. Here, our operator is dipole, which we defined on the previous slide. So we need to find expectation value, matrix element, between wave function at initial stage, when all electrons are on the occupied orbitals, and final state, when we promote electron from the occupied orbital to the unoccupied.
Oh, means here you are talking about like 0 point energy. Like this is E1 is it should be half h nu and
No,
E2
no,
should be
no, no, no,
half
no,
h
no, no,
nu.
no, Joanta, no, no 0 point energy today. 0 point
Okay.
energy is quantized nuclear effects. Right now, we are
Yeah.
looking only on electronic effect.
Oh, just only electronic things like only h nu.
So this h nu is light.
Mm. Okay.
Okay. So I am going to simplify my own life, and instead of Slater product, I will do just a Hartree product, because otherwise it will be too much writing. But the main idea will still be here. So ground state wave function of two electron system will be product of the electron number one sitting on the orbital one and electron number two sitting on the electron two. The dipole, if you have two electrons, will be, and we forget about nucleus, will be just position of first electron plus position of second electron. And then if we formulate the wave function of the excited state, then the first electron will be still in the orbital number one, but the second electron will be promoted from orbital number two to orbital number three. And we need to look for the consequences of this promotion. So why I am wasting your precious time and why I'm spending my time as well. This problem is challenging, and for Kristen, who already took PChem, and for Janice, who will take PChem, here is the comment. In standard quantum theory, one typically wants to deal only with one electron problems because it is so much easier. And here we need to find matrix element of at least two electron problem, or generally multi-electron problem. And it could become very challenging, but in the next few slides, we will see that the problem is automatically very much simplified. So we are formulating matrix element of dipole operator for the system being promoted from ground state to excited state. And this bra and cat angular brackets are equivalent to making integration over first electron position and second electron position. So the operator that will be in between is this summation of position operators for first and second electron. The initial ground state wave function is product of first electron in first orbital, second in the second. Excited state is first electron in first, second electron in third. So I am going to plug in all stuff in here into the equation at the top and see the consequences. And we are going to have good positive surprise. The situation will be very much simplified. So same things, just in the better typing. So matrix element, integrals over position of first and second electron, and then we have this bra and cat, and operator in between. So in its bra and cat, first part of the product is the same, and the second part of the product is different. So I'm going to open the brackets and take these integrals. And if you are tired or doing something else, you may lean back and relax. It is the technical details are less important. I will tell when it will be more critical to focus. So I am opening these brackets, which means if there is a summation inside the brackets, I can split overall integral on two terms. First integral when only the first term in the brackets plays a role, and the second integral when the second integral plays a role. And the bra and cat are the same in both terms. I'm going to utilize the orthogonality property, which means product of wave functions with two indices I and j will give 0 if indices do not coincide, and will give 1 if indices coincide. Now, let's look what we have in the first term. So when we integrate over the R1, we will keep the integration over R1 unchanged. But let me invite everyone to who is following, which is not as critical, to perform integration over R2. So if we integrate over R2, we have phi with index 2 and phi with index 3. So the indices here do not coincide, which means when we perform the integral over R2, over this phi 2 of R2 and phi 3 over R2, we will get 0. And then we do not care for integrating over R1. So the first integral will give 0 because of the orthogonality properties of these molecular orbitals. Now, let's look on the second term. So we again have two integrals over R1 and over R2. So I leave the integral over the variable that is inside for later, and yeah, I understand your breath. It's a few technical details, and I perform integration over R1 first. So R1 phi 1, R1 phi 1. So if I perform integration over these yellow things, integral over R1 of phi 1 R1 phi 1 R1, I will get 1, which means I can forget about all these yellow highlighted things and focus only on the integral over dr2. So I focus on this integral, this phi 2 R2, R2 in the middle, and here phi 3 of R2. So these three things need to be integrated. And before we go forward, I want to give a heads up. We have eliminated integration over R1. So from many electron integration, from many electron expectation value, we are moving towards one electron expectation value. So same thing in better typing. First integral yes, same thing. So the first thing became 1, and second one is just integral of this initial R1 to final R3. So with this derivation, we prove that the matrix element of the transition from ground to excited orbital is equivalent to matrix element of position operator in terms of one electron molecular orbitals. So it is really very important observation. It means that in the more complicated general thing, and for multi, like if there is a 10, 100 electrons, it will be still, one can reduce it to one electron transition between involved orbitals. So when we use this orthogonality, when we are considering optical transitions, we can compute intensity, probability of photo-induced transition from ground to excited state by evaluating matrix one electron matrix elements. So this, let me finish this little section. So this matrix element of transition from ground to excited, it is probability that the molecule will interact with the light. And if one takes this value squared, ground, excited, bracket, absolute value squared, it will give the intensity of the spectral of the line in the spectrum, or it is what is called oscillator strengths. So right now I'm closing this little section, but in about 2 weeks or less than 2 weeks, we will return to the subject, and it will be part of our practical things. Okay. Few more comments on the solids. So let me start another little discussion. So we all have discussed what is the molecule. Molecule is a collection of ions and electrons localized in one area of space, connected by bonds. But now let me ask what is the solid? So if you have general feeling or definition of solid, please type or speak. Maybe today the microphones are not always working, but Janice, I see you have unmuted microphone, but I do not hear. Maybe there is some technical problem. No, I still do not hear. Okay, would you, if you have an idea, would you please type briefly, yeah, yes, please do. And we are spending a little bit more time on these discussions, but I think it is it makes it more vivid and vigorous if we have a discussion rather than I'm mumbling boring things. Okay, so a little tournament. Who will type definition what is a solid, just in an informal way? Kristen, I see your microphone is unmuted. Do you have a comment, question, or definition of a solid? Okay, I do not hear. Joyanta? I know you are the expert in molecules, but do you have a feeling what is a solid? Okay, I think everyone is a little stressed with this concept. So, oh, okay, I see Janice. I will read out loud. So, for me, I believe a solid is a collection of atoms localized in a small area with a low kinetic energy such that they stay localized. Yes, you are correct in the following sense. In your description, you are explaining difference between solid, liquid, and gas. So if the kinetic energy is small, it does not melt and evaporate. But there is another thing. Probably the best question would be to ask for definition of a crystal. So if the mutual arrangement of atoms is repeated again and again in a periodic way. So, so suppose we have a solid crystal and we have two atoms. And then we can form this black box, and in this black box we have this red arrows showing the positions of these two atoms. So if it is a true solid periodic crystal, then we can make copy paste of this black box. Oh, I see a comment of Joyanta. Collection of atoms, ions, and molecules, not only atoms. Yes, yes. So let me continue. So if I copy paste this, I literally do it. Insert. Picture from file. So if I copy paste this black box, it will look absolutely equivalent to the first one. And this yellow atoms, so to say, will have the same coordinates in respect to the origin of the box as they had in the original box. Then one may define the size of the box in here is the green arrow, and we have the vector A. So if we define size of the box, then positions of the of these yellow atoms in the periodic replica in the periodic image in respect to the origin in the original box will be the same as they were in the first box, plus periodicity vector. So if you have this periodicity vector, then positions of ions in the next replica, so this image is called replica. Replica. are equal to original positions plus translation vector plus this size vector that defines the size of the periodic box. If we have more than one, if we want to prolong further, there is another replica next to it, and then positions of these yellow atoms in the next replica here and there will be same as in the original cell plus 2 times the periodicity vector, 2a. So the definition of solid is regular structure where position of any atom in the this large size object can be described as a replica of the very small initial positions in the initial unit cell. So the solid atomic structure of solids is obtained by translation of the original unit cell. And the connection to this concepts of solids is very popular in experimental physics and chemistry, and it typically connected to XRD, X-ray diffraction. So many of you have already practiced characterizing the materials with X-ray on the X-ray diffractometer, either operating personally or bringing it to the characterization center. At NDSU, it is Dr. Angel Ugrinov, and I'm sure that in UND and Los Alamos there is an X-ray diffractometer. So as soon as material is periodic, one can get its structure, characterize it in this way, and the main property is this translational periodicity. Please interrupt me by typing or asking questions if this concept is a little wild. So minimal configuration is repeated again and again. And now, if we quickly accept this definition of a solid, we may set up that potential of the acting on the electrons in the solid is the same as potential in unit cell, but in the replica it is same function, but it is shifted in respect to the potential in the original cell. So this red lines here correspond to periodic potential. When we have atoms, they do attract electrons, and centered at the atoms we have attractive potentials. As soon as we move, as we consider the different periodic cell, we have the same potential here, there, and there. And now for us as computational chemists, we ask a question: how does the wave function look at the atom in the next periodic cell, in the next replica? And the answer of this question was provided by Felix Bloch in form of a theorem, and he tells that wave function has the same absolute value squared, but if we do not do absolute value squared, if you look for a phase, then wave function shifted into the next periodic image will have a phase factor with this exponential imaginary unit k vector and then number of periodic cells. So if we want to describe electronic structure of periodic objects, we need to take into account the Bloch theorem, and we need to find a solution in the form of a Bloch function. So the atomic function in the vicinity of ion is the same, but in addition, there is a phase factor. And I know that it is very far from intuitive interpretation. So this phase factor should be interpreted as follows. It should be interpreted as the many electrons on all atoms are moving continuously with non-zero velocity. For Kristen, who took PChem, it will be very much related to the plane wave. And Janice will probably experience it in the fall. So phase factor. Okay. So I'm done with section on the periodicity, and now last section before we go to the practical exercise. I apologize, it took a little longer, but I think through discussion we got it better. So the subject, the little section that I'm going to deliver right now, was already presented by Kristen on our last presentation. So basically, the question is, if we start with a neutral molecule and then add or remove an electron from the molecule, how does the total energy change? And the question is, on one hand, trivial, because we do have the protocol how to take total energy out of the molecular system if you practice Hartree-Fock with Coulomb exchange. But the question is how to assess total energy in a quick, qualitative way. So the approximation is that Coulombic repulsion and exchange attraction between pairs of orbitals can be temporarily removed. So it will make it incorrect with high standards, but qualitatively it can still be a way to assess the properties of the system. So if you do it this way, then in the very, very rough and approximate way, neglecting 2 electrons contribution, total energy of system with n capital of electrons will be summation of orbital energy on each of the occupied orbitals. Now there is a, so here is the credit to Christian, and I just didn't have time to add credit to Kristen, but I give a verbal credit. So she already introduced this to us. The lines here show orbitals. Orbitals up to HOMO are occupied with pair of electrons. And then unoccupied energy is offset by the band gap. So the question is, what would be the energy, total energy of the system, if number of electrons is less by 1? So if we ionize system, so what is ionization energy, ionization potential? IP. Joanta, can you please comment how would you experimentally measure the ionization potential, ionization energy of a molecule? If you're interested. No comments. Anyone else wants to comment on the ionization energy?
Can it be measured electrochemically?
Yeah, I can describe.
Please do, please do. And Kristen, you already did it last week, so let's give Joanta a chance. Yes, please do.
I think in physics and chemistry, ionization energy or means like ionization potential. I think it's the minimum amount of energy required to remove the most loosely bound electron.
Right, but how do you find it experimentally? Which experimental technique do you use?
Which experimental technique to remove the electronic ionization potential measurement?
Which one?
Like for we were talking about how I will measure the ionization potential, right?
Yes.
Suppose.
So there are two things. One is photoionization, and another is oxidation and reduction energy in electrochemistry, right?
Yeah, definitely. So I think electrostatic potential you can through ionization potential, right? The term ionization potential also it can be used as instead of ionization energy.
Yes, yes. So when
I think you can calculate effective nuclear charge.
No. I'm talking about experiment. When you do cyclic voltammetry on your electrochemistry, right?
Okay. Yeah.
Then
this also you can, yeah.
Then this two
you can use, and then you can predict a little bit oxidation and reduction.
Exactly. And so it can be measured experimentally. And if you
Koopman through you're talking about not Koopman theory.
Right. And if you do it on calculation, the neutral system, anion and cation correspond to system when we have 2 electrons on HOMO, then cation when we removed 1 electron, and anion when we added another electron. And the difference is that for cation we remove electron.
So the basic thing is that ionization potential is the oxidation, nothing else.
Exactly. Yes.
And electron affinity is the reduction.
Exactly. Yes.
Nothing else. These two terms, it's completely correlated. Electron affinity is you have to add 1 electron to neutral atom, and ionization potential you have to remove 1 electron from the loose cell electronic structure. That's completely oxidation you are doing. You are going to do, and reduction electron affinity means electron completely tends to take electron affinity. It's completely reversal. Electron affinity and ionization. Electron affinity and ionization. It's oxidation and reduction. It's a simple thing.
Okay. Yes. Thank you. Very good. So number of additional electrons 0, +1, -1, right? And we have additional electron or lack of electron. So if we insert, duplicate slide, and remove all comments. Remove all comments. Oh no, it doesn't want to remove.
And different things is that the difference between electron affinity and ionization potential is that generally ionization potential is an endothermic process. Generally.
Good, thank you. So when we need to compute it, we practice this approximate equation by making summation over molecular orbitals. So if it is original number of electrons, we add together energies of molecular orbitals of all occupied orbitals up to E sub n, which is equivalent to HOMO energy. If we remove electron, we perform the same summation, but we have one less term. So this energy of HOMO is not present. We remove this electron, and therefore it is not entered into the summation. When we add electron, our summation goes over larger number of orbitals. So we place an electron onto LUMO, and we add the energy of LUMO into the total energy. So now I'm going to look on comparing the total energy of cation and neutral, and then compare total energy of anion and neutral, which can be done by subtracting. So if I subtract the energy of anion and energy of neutral, I will give this difference. So it will be minus energy of last electron, or minus energy of HOMO. If I need the electron affinity, I will subtract the energy of the anion and neutral, and it will be this one, energy of LUMO. So this conclusion that ionization energy is equals to energy of HOMO and electron affinity is equals to energy of LUMO is known as Koopman's theorem. So it is an approximate step, but it is possible to very quickly assess. So instead of redoing calculation with additional or removed electrons, one can approximately assess properties of materials just from one single point calculation. Okay, so I'm finishing this section. We are done with practical materials, and we are going to the, here's my typo. We are going to the practical thing. So to do practical thing, I invite you to open terminals if you are using the Mac, then it is terminal. If you are using Windows, it is MOBA Xterm, and we need to open at least two windows. One on the in one we connect to the photon, maybe even three, and on another connect to the photon once again. So let me check if we have connection for the voice, so that if someone has a question, I will hear it immediately. So maybe I will connect to this meeting from other device and make sure that we can
So actually, Professor Dimitri, I have to use both export and terminal, right?
Uh-huh.
I have to open both export and terminal, both, right?
Yes.
In macOS.
Yes.
So through export, I can write comment or in terminal. Export, right?
Yes.
Process completed shown means like I have to put again like SSHY, right? And then to connect with server, right?
Yes, same as you were doing while preparing.
Okay, then I have to connect with open it Gaussian, right?
No, do not connect. Do not go to Gaussian.
Okay. Just okay. So
I will instruct what to do, and
okay.
I hope everyone will. Okay.
Professor Dimitri could help me a lot actually because I just opened the notepad, means the Mac notes, so I can write it here instead of writing paper. I can write my things in notepad, and then I can copy to your export.
Yeah, that's good.
Yeah.
So I did type a command in the chat room. Please try to repeat it and let me what is going on.
Oh, this I have to write SSHI SS.
Yes.
This I have to write.
Yes.
Okay. Puri dot. What is this? Puri dot not.
Just copy paste.
Okay, okay.
Or
then, just copy and then I have to put in.
and then hit enter. Hit enter.
Okay, okay. Then in export, right?
Yes.
Export only. This process completed. That is shown here. Process completed. So just I have to comment and V, right?
Just when you are already on the photon, type this command. Yeah. Okay.
Just to photon means I have to go to SSHY and then I have to write it. Then come to photon, right? In photon means I have to go directly SSHY. Then your
Wait, are you on the photon right now?
Now I'm in the export.
Okay, open the X term, the terminal.
Yeah, terminal already opened.
Okay, in the terminal, are you logged into the photon?
In the terminal, okay. It means I have to put SSHY. Could you please copy it? That would be better for me.
Okay, I'll type it over.
Yeah.
But do the same as you did it for preparation of your talk. You should have it written somewhere.
Yeah, just you could copy it. SSH by cleaning at of photo dot node.nh, right?
I do see it is typed by everyone except Janice. Janice, were you able to log into this query? Okay, so then do cd to this directory and open a directory for open a subdirectory for yourself. By you see, I did open directory for myself, and you may do it for everyone. This is a different cluster, which is a little more powerful than Photon, and we should do exercise there because it will be more efficient. Okay, I see Kristen, Janice, you. So we have Dr. Yu Zheng and we have Professor Tao Yu, who has. Okay. So now we are waiting for Joyanta. Joyanta,
so already that came, that not Dakota State University clean method of photon already came. That I have to write.
Okay.
There I have to write CD spec, or I have to go to directly export from there.
No. If you are on this photon, then in there on a photon you need to type this. I did retype it. SSH space -I space tilde / You see it?
Yeah. Thanks.
Okay.
Yeah, that came, right?
Okay.
Yeah.
Okay. And then do cd space and then copy. I'll just copy paste the. C. Control V. So go to this space on the disk space, to this directory, and make a directory for yourself. So after you, did you do this CD?
Just 1 minute, because it will take a little bit time for me. Just 1 minute. Just have to copy the whole things, like CD
Yes.
/ global, all things, right?
Exactly.
Okay. Just you could do it for me. One thing, just those comments, please write it in notepad and send it to me.
Oh no, we are recording things, and you can copy the chat room yourself.
Okay, thank you. Yeah, Summer, that came Summer, right?
Okay.
Yeah, that
and
came.
And now there you need to create directory for yourself, like make directory mkdir space and then your name as you want to spell it.
Yeah. Okay. Okay, that came. Yeah, Summer.
Okay, excellent. So it is our meeting, I would say web 16. And I will copy sample files to work on which were pre-made, and then I'll give explanations.
So then after that, what I will write?
I'll tell what to do. I'll tell what to do.
Okay.
Just wait.
Okay, thank you.
Okay, so please copy from my directory this files titanium4.xyz, and originally we should draw and borrow it from the previous lab, but then time will run out. So I will explain what it is in a second.
You could please copy paste in chat room.
Okay, I did. So I'm going to make TOP to prevent automatic log off, and I'm going to show slides for very brief introduction. So we
Okay, Professor Dimitri, that came like global CFS, CDRS, a lot of things came. So after that, what I'll do, MKD also that I already copied and pasted here, and that came here, killing at the rate of Cori 01 global CFS slash CDRS, a lot of things. XYZ.
XYZ, yes. I'll inspect your directory when it will be time. Now let me tell something to everyone. So these slides look a little bit ugly, but I did them in 2011, but they used to be working. It was handwritten suggestions that I gave to my first graduate student, and now she's a postdoc at Wake Forest University. So the software that we are going to practice is called VASP, Vienna Initial Simulation Package. Unlike Gaussian, it has 4 input files. And in Gaussian, everything, all input information is stored in the .com file. In the VASP, we have 4 files for the following purposes. So position, postcar, is for coordinates. In-car is telling what to do. K-points is related to Bloch theorem that we discussed 20 minutes ago, and I will provide templates at the beginning. And podcar is analogous to effective core potential, so it is specific of atoms, telling something about potentials. So we need to create all these 4 files, then run and analyze the outcome. And through iterations, we'll get practice in what is going on. So the let me go immediately here. Yes. So the main feature, which is plus on one hand and difficulty on another one of the VASP software, that it is designed for periodic boxes. And therefore, if we create an input file, we need to assume that this molecule will have its periodic replicas. And if we do not want the replicas to clash into each other, we need to set up a vacuum. So we need to explicitly tell how many vacuum we have around our model. So this is the main feature. And I will return back to these slides in a minute. Let me show practical steps. So I'm going back to terminal, doing Control C to stop this TOP, and I'm going to process the file code. Let me check WC titanium 4 something, titanium 4 without something. Yes. So I'm doing sort titanium 4 dot xyz into the file which I will call postcar.xyz. And let me copy paste this command. I will do several steps and then inspect the directories and make sure that things are working. Okay, so then I'm opening this postcar.xyz, vi postcar.xyz. So first line is.
Professor Dimitri, just have a question. In like in my comment, where I'll put it in your last command. Like in my case, that came VASP came 676 Summer CP Dimitri Lab 16 star XYZ. Then I will write it that command, right?
Yes. So when I will go to Jonathan, just wait a second. Just wait a second. I will want to give instructions to everyone, and then I will inspect your directory personally.
Okay.
So I'm opening this postcard.xyz with VI editor and make sure that the first line shows number of atoms, and then there is an empty line. It is important, and then all atoms are sorted according to the type. So when we are in the Gaussian, they can be in the random order, like hydrogen, titanium, oxygen. Here it is important that they are organized. And then the next step is bin rotate XYZ. And after this command, I hit enter, and then I hit 0 enter for 3 times. 0 enter, 0 enter, 0 enter. So this is important because sometimes per unit cell needs to be changed. One needs to change angle. So these 3 parameters that were set to zeros were angles. If I want to rotate the periodic cell. Just wait. I will give one more command and then go to your directory. And then,
okay, thanks.
Not a problem. And then after completing the following command that I'm typing to everyone, there will be ls-ot, there will be a file called postcard. So if you have successfully generated it, please look inside this file. We may need to recreate it and improve it, but just look inside and make sure that it's not a big shock and surprise. It will be looking very different from what we saw before. And I will make a little journey over the directories to make sure that everyone is doing good. So let's go to join enter. Joenta, you do not have anything.
Yeah, so how I'll
no, just I will type command, so copy. I suggested that you borrow files from my directory. 4.xyz space here. ls-ot. Okay, so can you do? I will retype. Can you type the command from chat line in your directory?
This is right. Sort TI4
yes.
No.
Yes.
This is sort TI4.
Yes. Yes. Yes.
Okay, just wait. No such file on directory.
Come on. You are in the wrong directory. Can you please type pwd?
pwd. Yeah.
Yes. And copy to the chat line what you see.
This is right. Sort pti4. This is right. Sort ti4.
Can you please share your screen?
No such directory here.
Can you please share your screen?
Just wait.
Are you sharing your screen right now? Jayanta?
Yeah, you are getting or no?
No, I do not see it.
Okay.
So at the bottom of the communication software, there is there should be like microphone, camera, then disconnect, and then there is a button for share screen.
But here I'm not getting share screen. Disconnect. Do you really want nothing? Cancel. Disconnect. Nothing. Cancel.
No, after disconnect.
After disconnect is in no such button.
Then please reconnect using different browser like Chrome or Firefox.
Okay, that's fine. But the thing is that what I will write here for like summer, I am just here killing at the Cody 01 slash global CFS CDRS M1251 dash CHEM676 summer. Then what I'll do?
Then type cd space Jayanta. Go to your subdirectory.
Okay. CD space just do it. Okay, means like oh, here like previously scratch that I put in for
yes.
X squad, not here X scratch. I have to just put CD Jointo, then go to here and then PWD, right?
So if you type PWD, what do you see now?
PWD, nothing. Here just Summer Jointo came.
Okay, now please type this sort. Please type this command sort space TI4 point. Do you see it?
Just have to put short.
Yes, this line, copy paste.
Just wait, copy. Yeah, postcard where that came TI4 XYZ. Then.
Okay, very good. I see you did it. Now you need to type vi space postcard.xyz.
Good, please write here vi.
Yes, vi space postcard.xyz.
Then came here.
So type dd.
dd.
Yes.
Where?
Just as right after it did your cursor, your marker is showing the first line. It is empty. You need to delete it. Type dd.
Where?
Just type on your keyboard 2 letters D after one after another.
In 18 H where postcard after postcard or
did you type vi postcard.xyz?
Yeah, here na postcard XYZ 20L1067, lot of things.
What do you see?
Nothing else here, just
you should see numbers.
Yeah, number 18 H.
Yes, very good. Can you please type letter D two times?
D.
Good.
Yeah.
Now.
So that came TI.
Now type letter I.
I means capital or
no, lowercase.
Okay.
So on the bottom of your screen, there should appear the insert mode. Now,
insert mode came.
Good. Now move arrow down once.
Where?
Just arrow down once and then hit enter.
Arrow down one.
Lower right lower edge of your keyboard, the arrow, the direction. Just move cursor one line in front of the first hydrogen.
Okay, means here, here, 1H, 18 1H. Here.
So
and then
type enter.
Enter.
There should be empty line between 18 and H.
Yeah.
Okay. Now you need to type key escape.
Like
on the top, escape on the top, ESC on the top left.
Okay.
Then shift column.
Escape already I put then.
I did type it. Escape column, shift column.
I have to write comment here. Comment.
Sorry, I will retype it. ESC column WQ and then enter.
Oh, means here I have to, okay, just have to write the comment here, right? Escape colon WD, right?
So after you hit the escape button,
okay,
the insert mode disappears.
It
then
already disappeared.
Now type column.
Now type
symbol of column, 2 dots, one under each other.
Where actually in before 18 or
no, just type it on your keyboard. It will appear in the lower left.
Lower left, right?
Yes.
Okay. Colon.
And then lowercase WQ.
Yeah, WQ. Yeah.
And then enter. And then enter.
Enter CHEM. Oscar XYZ CHEM.
Okay. Let me see. Okay. Not so bad. You erased one more line, but I see the connections. It is now on the screen. Let me clean after what you did and make it a little better, but do not do anything right now.
Okay.
I will reduce things. So if you see on the screen, I'm doing these things. VI postcard.xyz, right? Just watch, do not do anything.
Okay.
So deleting top line, DD, then typing I, going in front of hydrogen, enter, maybe space, and then after this, I am typing the escape, so the word insert disappears, then column WQ, enter. More postcard.xyz. And now please repeat same as everyone else did. So I will retype the commands. First this bin rotate, and then Perl. So these 2 commands. So Jayanta, now I need to focus on others. So please give me some time.
Okay, just have to write it here, like /bin.
Yes, these two commands that I did type, you need to practice it in your directory.
Okay, like angle of rotation in degrees, and then
0, 0, 0, 3, 3.
Okay, and then I have to put before 0, 0, 0 or all
0, enter, 0, enter, 0, enter.
Okay, so before that I have to write think XYZ postcard, then 0 enter, 0 enter, 0, right?
Yes. Okay. Now I am in the directory of Genis, and I do not see. Oh, okay. Now I do see it. But the file more postcard. The file is empty. So Genis, I'm in your directory, so you type bin root. Oh, wait. Let me check once again more. Postcar. So if the Janice, you didn't modify your postcard, so please open the postcard in the VI, or if you, I don't know if they have Nano. Nano is a little more user friendly. No, it's not installed. So open your postcard in VI and do the same thing as Gianta did. So remove the empty line at the top and add an empty line between number of atoms and first hydrogen. And after that, save and exit. So I'm watching. So Janice, if it doesn't work by some reason, please type what is the problem. I don't know why the voice connection is below standards today. Check now. Okay, I'm checking. But you did you did delete one hydrogen. One needed to right now the stoichiometry is distorted. So let's do it over. So as a history, I will copy this postcard XYZ as history .xyz, and now I remove this postcard.xyz and do it over. So your file, just in case, is stored. Sort titanium 4.xyz into postcard.xyz, and I will do it myself now. So postcard XYZ. Oh, maybe you are already know. Then I will exit.
Could you please go my file?
Wait. I'm busy with Janice.
Okay.
So Janice, I'm going to open. Oh, you are going to redo it. Okay, then I will not touch it. So I did recreate, and you see there are 4 hydrogens, and one needs to insert an empty line between 18 number of atoms and the first lines with coordinates. Okay, let me more. Perfect. And after this, yes, I did double check. After this, please practice this rotate command. So right now, before you redo it, I see this rotated files are as good as empty. They're like 13 symbols, which is not right. Yes, minus AT. Janice, were you able to practice this rotate command? Just okay. Okay, now I see this Pascal rotated has this 1300 symbols. And after this, please practice this Perl command. Not yet. Kristen, I have to leave for another meeting. I was having trouble with rotate command, so I will plan to set up a meeting with you. Kristen, if you really, okay, I'll probably, if you need to depart, then please do. Let me go to your directory quickly. Please. Oh, more postcard. More postcard. So, Kristen, you need to insert an empty line between 18 and the first hydrogen. If you're still here. So you can do it yourself, or I can do it instead of you. So rotate command will not work if the .xyz file is not in the right format.
So actually, Professor Dimitri, in my case, it came vi postcard.xyz.
Wait, Janice, sorry, Giant, I need to go over directory of everyone, and then I will return to you. I apologize, but we need to go through this. So, in the directory of Kristen. Oh, okay, yes. Yes, and now after this, the rotate command will work. So after the postcard is in the right format, you just repeat. Yeah, Kristen, your postcard file is normal, and now if you type this rotate command, it should be correct. Or I can type it myself. Bin rotate xyz. And then after you start the command, you type 0 enter 0 enter 0 enter. So rotate x y z, and then 0 enter 0 enter 0 enter. No, it gives. Okay, I'll fix it. Just a second. Oh no. Insert, enter, escape, right quit. Rotate, 0 enter 0 enter 0 enter. Okay, done. ls minus ot. Kristen, your file is ready at this stage. If you need to, I do not want to you to miss your other meeting, but let me type in this command ls minus ot. So now you are on this. Your directory is on the same page as everyone else. More postcard. So it is what all of us should have. So I'm going to next next directory. let me go to, oh, sorry. Mm-hmm. I'm in the directory of U. More force car. More force car. More. Okay. Hydrogen, oxygen, titanium. Okay, everything is good in U directory, and going to the professor Dell. More force car. Okay, good. And now I'm going to my own directory. Okay, so I know that we cannot do it too far over the time, but let me give comment of what we were doing. Yeah, so this command, so Perl is just a language, .pl is a script, postcar underscore rot ting is what comes out of the rotation, postcar is what is the output, and this 000 is amount of vacuum that I was introducing in the slide. So this amount of vacuum cannot be zero. We need to specify certain amount of vacuum, delta x, delta y, delta z, in order to prevent molecule interacting with each other. So between last atom in the original cell and the first atom in the periodic cell, there should be a vacuum. So this the amount of this vacuum is must be equal to infinity if we describe the molecules, or bond lengths if you describe periodics. So if suppose I consider this molecule as a molecule without periodicity, then infinity, like 7 angstrom, is a good approximation for infinity. It is good to take like 10 or 15, but then it will slow down calculation. So I'm retyping the last. Command. Yeah, Janice, it's not a problem. We'll continue on Wednesday. Thank you for joining, and there will be recording. So replace 000 with 777 and do it once again. So now I'm looking on the postcar file and trying to interpret it. So first line is the list of atoms that we have. The line number 3, 4, 5, 6 is stoichiometry. So we have HO titanium. 4 is number of hydrogens. O is number 10 is number of oxygens. 4 is number of titanium atoms. Second line, the 1 is a scaling factor. One may need it if one looks for strain of a lattice. Right now we just keep it 1. Then there is a box 3 by 3 matrix. So this shows the size of the box. So again, back to this box. The size of the box after we have added the vacuum. So in our case, for this molecule that we are describing, the size of the periodic box is 14.5 in X, 14.5 in Y, and 11 in Z. So we are considering a box of this size in angstroms. Now there are a couple of service words, and then there is a set of coordinates. So do you see any coordinates being smaller than 0? No one? No. Thank you.
No. Yeah.
Do you see any coordinate being having value bigger than 1?
No.
So how to interpret? We definitely, if you describe a model, we need for each atom we need 3 Cartesian coordinates, X, Y, and Z. But we know that for this model, it's titanium hydroxide. Even single bond is longer than 1 angstrom. So it's probably different units. So what are the units for coordinates? Why they are between 0 and 1?
It's in the K space?
No. Yes. U is telling that it is relative. And there is sometimes people use the word fractional. So fractional coordinate, which means if we want the first hydrogen atom and we want X Cartesian projection of the first, then we take size of the box in X direction and multiply it by this fractional coordinate, 0.75 times 14.5. And then it will give the X Cartesian coordinate of the first hydrogen. Then if we need the Y coordinate of this first hydrogen, we take its 0.75 times size in Y direction, and it will be Y coordinate in angstrom. And if you need Z, we take this fractional coordinate, multiply it by size of the box, and we will get a value of Z coordinate. So this is done in purpose. So that the code will be universal for any size of the periodic cell. The coordinates will be of the same format and same level of digital precision. So we are in units of the cell It's fraction of the cell. How far from left to the right of the cell. Now there are 3 letters T, T, T. Definitely it relates to the atoms, but what this letters T may mean? Any suggestions?
Translation? Oh.
Super. Yes. So it means if we run optimization job or molecular dynamics, we will allow for each of Cartesian projection to translate. If you want to freeze any atom or any of the Cartesian projection, we will replace it, the letter T, with letter F. Freeze or forbid. So first letter corresponds to X, second to Y, third to Z. So if you want to allow first hydrogen to move in X and Y and fix its Z coordinate, we will replace last T with letter F. Okay. And escape. So copy from template from bin points space period. I will need to redo it when we meet next time for those who has already disconnected. But so the K points is a standard file we are not going to discuss. I just provided the template. So using template is fine. Same for the in-car. So bin in-car geometry optimization period here in-car. So it will be too long if we discuss all details, but let's just copy the template. And later on, it will be one of the important tasks to discuss what each of the lines in this in-car file means. And the third one is so-called K points. So if you go back to the slides, and we are very, very close to completion. We will finish in like 5 minutes. So we need 4 files. Postcar, we have it. In-car, we have it. K points, and we miss only pod-car potentials. So for potentials, it's one needs to do a little labor, but it's quite logical. So I'm type module show wasp. My fingers do not hear me. Module show wasp. So it shows in which directory the service files are located, and it shows pseudo potentials directory. So I copied. Control C. Now I'm doing head postcar. So we need potentials for hydrogen, oxygen, titanium. CAT for concatenate. Pasting location of pseudo potential. Selecting PBE functional. Selecting hydrogen atom. Typing pod car. Bigger. Pod car. Then doing the same, replacing hydrogen. Sorry. So doing first for hydrogen, then replacing hydrogen with oxygen, and then replacing oxygen with titanium. So I will copy paste these commands into the chat line. So after these commands, we do have, see the last 4 files that we have is 4 files that are needed to successfully run WASP. There is a just very short addition to launch the job through job scheduler, but since majority of students did left, I suggest we postpone this operation to the next meeting.
Sure.
So let me ask for questions. You, Tao, and Jayanta.
I have a question. Could you please go my directory?
Okay. And just a second. Grep PBE pod car, just checking, and then it shows it has PBE for hydrogen, PBE for oxygen, PBE for titanium. It was just a check that pod car file is healthy. Okay, I'm going to the directory of Joyanta, -OT, postcard. So, Joyanta, you need to just type. You need to type. Oh, no, I don't want to type it instead of you. You need to do it yourself. Copy the template of key points. Copy template of the in-car.
Okay.
Control-C. Control-V. And then create the pod car file by doing three commands one after another. So first, potential for hydrogen. Second,
This all cat global. All
yes. And then I am redoing it 3 times, but if you see, I'm changing only 2 letters for name of the element. And after so you have key points in car, and you are building pod car. Grep PBE pod car. It looks like you already did it for hydrogen and titanium, but you didn't do it for oxygen.
Please write it. Grep PB pod car.
It is just checking. So it looks like your pod car includes potentials only for hydrogen and titanium. So
yeah, then title PB hydrogen is 15 June 2001.
It's just a check if you have a good pod car file. Let me do it. Just watch me. I will remove pod car that you have created and redo, because order does matter. So rm pod car. rm is remove, and try not to use this command. So rm. Now,
and no such file in directory.
Yeah, because I did remove it in front of you. Now, do not type yourself. I will type it. Just watch. So first, hydrogen. Second, do not repeat this command. Just watch me. Second, oxygen. And third, titanium. Okay, and now if I type this grep PB pod car, it shows first hydrogen, second oxygen, third titanium. If I type head pos car, oh no, something is wrong with your pos car. I need to fix it as well. More postcar.xyz. You did remove titanium atoms at the bottom. Your model has only hydrogens and oxygens. Let me redo it. Sort titanium 4 into postcar.xyz. vi postcar.xyz. Removing first line, go into insert mode, And then I'm not erasing the last 4 titanium atoms. I am typing escape, column, right, quit. Now I'm doing rotate, beam rotate, beam rotate XYZ, 0 enter, 0 enter, 0 enter, plus minus OT. So the postcar underscore ROT has 1381 bytes. And then I'm doing this Perl bin tink to wasp postcar. Yeah, thank you, Tao. See you on Wednesday. Postcar underscore rotate postcar 777 plus minus OT head postcar. Okay, yep. So in here we have the list of atoms: hydrogen, oxygen, titanium. When we do grep PBE postcar, not PBR, PBE, it's Perdue Burke Artsarhov. PBE. We have the same order: hydrogen, oxygen, titanium. Everything is good. So your directory is in the perfect situation.
Okay, thank you.
Yeah, thank you. You may disconnect if you want. I want to check with Dr. Eugene if things are going well and if any help is needed.
Okay, see you later.
See you. Thank you for your dedication to the class.
Yeah.
Okay. Grep PBE postcar. Oh, you is not correct. You typed each command twice. So I suggest we remove postcar and repeat the commands. So what is shown here? It looks like it is for 6 elements in the model. So I don't know if sound works well. We can try to speak. If it doesn't work, I'll fix things. So let me check once again. Aha, you removed postcar. Very good. And now let's repeat these lines for accumulating potentials 3 times in the same head postcar, in the same order as a list of elements. So once for hydrogen, once for oxygen, once for titanium. And you know that we do not need to retype things. Just with arrow up, one can rerun the stuff. Okay, hydrogen is there. Good. Oxygen. It looks like you, after oxygen, you did hydrogen once again. So the bigger part means like append, add more to the same file. So let's remove it. Let's remove the postcar once again and redo, because the 3rd element should be titanium. Yes, thank you for removing it. Okay, hydrogen is there. Next will be oxygen. Oxygen is there. And titanium is there. Perfect. Yes. So your directory is absolutely ready. Not a problem. Not a problem. It's good. next step will be to submit job to job scheduler, but let's maybe wait until Wednesday for all students being here. So many thanks for your dedication to these meetings, and I believe we are done for today. If you have questions, let me know, and if this communication, if needed, we can set up a Skype if you need to discuss something. But okay, yeah. Then have a nice evening, and see you on Wednesday.